Okay, let's get to it. Let us go ahead and finish the 5.2 notes. And what was this? Nope. What were these notes called? Like trig identity proofs or some stuff like that? Proving trigonometric identities. We only have these two questions left. And like I said, we'll just spend the rest of the class basically cracking open the book and saying, well, how would we do this? And we'll take it to a certain point, and then we know, okay, as long as we know we could have gotten to this point, it should be pretty easy to finish it. Now, unfortunately, trig proofs are one of those things that really, honestly, the more you do, the better they get. I mean, and I don't like to say that kind of thing as an educator because it really frustrated me as a student to hear like, oh, well, the only way I can get better, the only way that I could actually know how to do this is if I had done a bunch of them. But how do I do a bunch of them if I don't know how to do them? You know what I mean? So, like I said, that's why I'm going to do my best to just tell you the ways that I would have approached a proof and why I would have done it that way. And that doesn't mean it's the right way. I'm going to be honest with you. The first time I did the one that we're about to do, I hit a brick wall. And it was like, man, that didn't work at all. And I honestly just had to scrap it all, not in front of a class because I did it ahead of time, but I had to scrap it all and try again. And then I got it right. But, it just happens and you have to not be afraid of that occurring. So we grab handy dandy, brand new, that's right, a light blue pen. Grab some other colors while we here. All right, I think we're ready to rock and roll. So we are going to prove that this side of the fraction equals, or this side of the equation equals this side. Now you can see the title. The title says working from both sides. Now I told you yesterday that you're not allowed to do something to both sides of the equation. But what I meant by that was you're not allowed to treat it like a scale where whatever happens to one side happens to the other. Because when you do that, you are making the assumption that they are already equivalent. Instead, what we're going to be doing for this question is we'll be doing things to this side, and we'll be doing different things to this side to try to show that eventually, yes, they are the same thing. So that's allowed. Let me tell you how you'll know that you did the one thing wrong that you're not allowed to do, which is work on both sides with the same operation. Like, oh, I'll square both sides. You can't do that. You will know that you did that wrong and that you accidentally made that goof because at the end you'll get something like 0 equals 0 or 1 equals 1. And that makes you feel like, yay, I did it. But that's the dead giveaway that you did it the wrong way. You're not allowed to do that, which is a lesson I learned hard in college. So without further ado, let's tackle it. Let's start on this side, okay? Cotangent squared plus 1 plus cosecant. Or cotangent squared over 1 plus cosecant. What can we do? What do we see?
I mean, 1 plus cosecant. Cosecant is pretty close to an identity.
Yeah, 1 plus cosecant is pretty close to an identity if it was cosecant squared. And is it 1 plus or is it 1 minus?
1 minus.
Is it 1 minus? Look, I'll be real with you. I don't know. Okay? And that's because I haven't bothered memorizing those. Instead, when I need them, I just write, and I'm going to write theta if you don't mind instead of u. When I need them, I just write cosine squared theta plus sine squared theta equals 1. And I go, all right, I know I'm trying to get a cosecant, which is 1 over sine. So I would then divide everything by sine, which is what you saw me do the other day. This is how I derived them. Because I honestly don't know them. I don't feel a reason to have them memorized when I could just build them anytime I want. I mean, what I'm doing right now is quick, it's simple, it doesn't feel like it's a waste of time. It just feels like, yeah, I understand why these things are true. So, yeah, it's not 1 plus cosecant, and it's not actually 1 minus cosecant. It's cosecant minus 1 equals cotangent squared. You see that? If I subtracted 1 from both sides, I would get cosecant squared minus 1. I don't really have that, and I don't want to have to multiply by its conjugate and then factor out a -1. That feels over the top. But look, that doesn't mean that this was a waste of my time because check that out. There is a cotangent squared right there. There's a cotangent squared right there. I can easily isolate this cotangent squared like we did yesterday or a couple days ago, I can't remember now, by subtracting this 1 from both sides. So I'm going to do that. I'm going to replace this cotangent squared u with cosecant squared u minus 1. That'll be step 1. So yeah, like I said, subtract this 1 from both sides, and you'll get cotangent isolated. So we can replace it with cosecant squared minus 1. Now, would it have been wrong to do what Max and I talked about, which was to multiply by the conjugate and then factor out a -1? No. Like I said, there is a lot more than one way to approach these things. I just felt like this was easy, excuse me, easier than having to distribute this to the conjugate of that. This just seemed easier to me. Okay. Looking at this, and we just used the Pythagorean identity here, so we don't want to try to use another Pythagorean identity. So I would be looking for ideas from the crowd. Like, what do you guys just? It's okay to be wrong. I mean, even what Max said wasn't wrong. It's okay to have a thought and try it, and sometimes it works and sometimes it doesn't. Just what would you guys try next if it was you? What would you try to do? What do you see? What do you know you could do? Anything like that? Okay, we cannot cancel these cosecants here because the pluses and minuses are stopping us from doing that. The only time we can cancel on the top and bottom is if we have objects separated by multiplication dots. But, Leilani, what do you think?
Could we take the top one and make it cosecant u minus 1 times cosecant u plus 1?
So Leilani is saying that this is factorable, that this is a difference of two squares. And if we factor this, one of its factors is right here. So that's very useful. So let's go ahead and try to tackle that. So cosecant u plus 1 times cosecant u minus 1. And all of that is over 1 plus cosecant u. Like addition doesn't care about order, so cosecant plus 1, 1 plus cosecant, they mean the same thing. So boom. What we have found out, and I've kind of snookered myself on space here, is that the left side is equal to cosecant u minus 1. Get skinny, math. There, I fit it. So yeah, we now know that this side equals cosecant u minus 1. So the reason why we're trying to approach this equation from both sides is because it's actually pretty difficult to see the steps in logic required to turn this into that. It's possible, but it's kind of difficult to do. I mean, how would you even thought to make the moves that you need to make, something like that. The point is, now that I know the left side equals this, I want to take this and try to also make it equal cosecant u minus 1. And if I'm successful with doing that, then I know that this is a true statement. We go. Well, we know it's true because we've been told to prove that it's true, but the point is do you know how to demonstrate that it's true? Okay. So, and you know what? I'm looking at my notes, and I think that I worked it too difficult. I don't know. All right, so I'm going to take a step down here, and let's start tackling this side. I'm going to leave some space here in case I need it, in case I need to manipulate this a little bit more. We'll just see. And if you're wondering what I'm talking about, why would I even bother manipulating this more? Well, I don't know if it's going to be necessary, but I do know that cosecant u is 1 over sine u. Remember I told you it's often pretty beneficial to write things as fractions and then find common denominators. So I may or may not need to do that. Let's just find out. I'm going to be real here. I'm about to step off the beaten path, and I'm going to deviate from what's on the paper next to me because I think there's an easier way. I could be very wrong. Let's find out. Okay? All right, what am I going to do on this side? Well, what I notice is I see a lot of opportunities for finding fractions and tackling common denominators. That's what I see. I mean, cotangent, secant, and tangent can all be written as fractions. So I want to see what's up there. So on the right side, I have, you know what? I'm going to do the right side in green. Just feeling special right now. Oh, buy more. cotangent u, and then I have secant u minus tangent u. See what we can do here. And honestly, I don't know if I'm going to need this space or not. Let's just see. Well, cotangent, cotangent is cosine over sine, right? Yeah, no, I'm sorry. I'm thinking. I'm trying to make chess moves here. I'm trying to look ahead and see what's going to happen when I go to do this. Because what I'm about to do is I'm about to distribute some stuff. And I was wondering if I should write them as fractions first or if I should distribute first, because what's going to happen when I multiply cotangent u with tangent u? Well, well, what relationship do cotangent and tangent have?
The inverse.
Not inverse. Reciprocals. What do you get when you multiply reciprocals? Not zero. 1. So if I distribute cotangent right now, I'm going to get a -1 right here. And I'm just trying to see if I should do that first or not.
Oh, yeah, because this is cotangent.
Well, I don't know. Let's just write them as fractions and see what happens. So cotangent is cosine u over sine u. And inside here, secant is 1 over cosine. Ooh, interesting. Okay, when I distribute there, my cosines are going to cross cancel. And we already know that this is going to completely disappear because it is a reciprocal. Grab purple. So yeah, we're going to distribute here and here. That purple's vibrant, isn't it? I'm going to have to try not to use up too much space here. I'll show the steps. Cosine u over sine u cos u minus, can I just write 1 here? Do you guys mind? Cos u over sine u times sine u over cos u, and they're just reciprocals. So -1. And looky, looky. Whee! So there has to be something on the top of that fraction. It's a 1.
1 over sine.
It's 1 over sine. So I have 1 over sine u minus 1. Hey, wait a second. 1 over sine, that's cosecant. Yo, we're done. Yeah, that's a lot easier than what's on my notes.
What do you do on your notes?
I'm going to show you in just a second once everybody gets finished. But yeah, that's always a viable method. It's always a viable method. As long as you're not doing the same operation to both sides because it's quote unquote happening to both sides of the equation. You're not allowed to do that. Yeah. Yeah, it's kind of like if you remember your geometry proof days where you could see how to start a proof and you could see the end of the proof. If you could make the two meet in the middle, then you were golden. And this is basically what we did. We made these two meet in the middle. Okay. You sure you got it? Okay. Okay. So is everybody finished writing it so I can show you what I had on my notes? Like I said, I'm kind of full of myself. If you didn't know that, and I like to do my things without looking. I know, shocking, but I like to do things without looking at the books because honestly, I don't even have teacher editions of textbooks because I don't need them. Okay, that's just how I think, and this is how I have this proof tackled in my notes. So I got to here, like we did today, and then for some reason I was forcing it to equal something else. So I changed my cosecant into 1 over sine, and then, no, this is the -1 right here. And then I went super extra, and I factored out a cotangent u, which left me with this ridiculous stuff. And then I tackled this side and it was just, I mean, oh my gosh, it's just, yeah, no, what I just did here is so much better, so much easier. And like I said, I didn't look in the book, so I don't even know what they did. They probably did it this way because it seems like the smart way. What I did seems like the gifted way. This looks like the smart way. Gifted people don't understand what you just said. All right. Gifted people go work. Smart or hard, who cares? Alrighty, and the last one of the notes, unless you have questions about this one, of course, you speak up to me. No? We good? You stressed? You look stressed. You okay? Okay. Working with common denominators. Oh boy, got some stuff going on here.
Wait a sec, what? Where's the common denominator? What?
Yeah, he says, where's the common denominator? Remember what I told you that 1 plus cotangent is cosecant squared, yes. But we have this 1 minus cotangent. Well, I'm pointing like you could see it. We have this 1 minus cotangent there, which we actually don't have an identity for. And even if we factored a negative 1 out of it, it would say cotangent minus 1. So again, we don't have an identity for that. So while McKinley's correct, this is an identity. It wouldn't actually help us much. Could we use the fact that this is cosecant squared? Probably. I mean, if you want to try to tackle it that way, I'd be happy to. That's not what's on my notes, but that doesn't mean it doesn't work. I mean, I'm always happy to check out a different way of doing something. In fact, it seems interesting. Would you guys be okay with me attempting to do it with this Pythagorean identity and it maybe not working and you seeing me have to start from scratch and do it a different way? Be aware, if that's the case, you're going to have to add something to your notes. I have the benefit of just grabbing a piece of scrap paper. So I think I can make it work. I really do, okay? I think I can make it work. Let's use a Pythagorean identity. We're seeing that this is cosecant squared theta. I like that. I like that. So let's just jump right into that. Let's say we have 1 minus cotangent squared theta over this Pythagorean identity, which we have on the top of our paper, is equal to cosecant squared theta. All right, well, where do we go from here? Well, I told you one of my tricks in the old bag of tricks is if things can be represented as fractions, usually that's beneficial. Let's give it a shot. And that's going to happen both on the top and bottom of this fraction, because cotangent is cosine over sine.
That's the side, not the cotangent.
No, I'm replacing cotangent with the fraction that it equals. Now on the bottom, I have 1 over sine squared theta, like that. When you divide by a fraction, the old keep, change, flip, right? Dividing by a fraction is actually multiplying by its reciprocal. But what is the reciprocal of 1 over sine squared theta? Yeah. Yeah, sine squared theta over 1, which is just sine squared theta. So I'm going to write, and if you're okay with it, I'm going to put the sine squared theta in the front because multiplication doesn't care about order, times 1 minus cosine squared theta over sine squared theta. Ooh, I am loving this. This is going to look, if this works right, the way I'm seeing it in my head, this is going to be so much more elegant than what's on my notes. I'm going to distribute this sine squared theta. Why would I do that? Because I'm seeing the chess move. I'm seeing ahead that if I distribute that, we're going to get a cancellation here, which is great news for us because we are trying to get things down into terms of only cosine. You see that? You see, you're allowed to know where grandma's house is, right? You can know where you're going. You're going to a place where there are no signs. S-I-N-Es, not S-I-G-Ns. Okay? So doing this right here will eliminate some signs, which makes us super happy. I'll show the work, though. Gives me sine squared theta. Oh, yeah, this is going to be so much more elegant than what's on my paper. Oh, I'm so excited. Minus sine squared theta cos squared theta over sine squared theta. Obvious cancellation. right? Deuces. Getting me to here. All right. We are legitimately one step away from our answer here. What I need you to see is how similar where we are and where we're going are to one another. It already says minus cosine squared at the end, like this one does. The difference is this one has a 2 in front of it. So where the heck did we get another cosine squared from, is the question. What do you think, Caleb? Sine squared plus cosine squared is a Pythagorean identity, but that doesn't mean that Pythagorean identities are useless to us right now. You're not wrong about that. I could factor out a negative, but if I factor out a negative, all it's going to do is change the order. It'll still have a minus in between them. How about I take us back to the, instead of the top of the paper, I'll take us right back up to here. And I will write cosine squared theta plus sine squared theta equals 1. I'm just reminding you what the Pythagorean identity is. Okay, would it be useful to do what? Right? Well, since we're trying to get to a place where there are no sines and only cosines, we clearly need to replace this sign with something. No, we could not its reciprocal so much, but what Breyer was saying was we could, yeah, we can isolate this and substitute in for it is what Breyer was saying. So we know that sine squared theta is 1 minus cosine squared theta. And you could take that which came from our first page of Pythagorean identities and you could drop it right there. So we will replace that sine squared theta with 1 minus cosine squared theta. This is this. It's been replaced. Oh, and by the way, here's the other minus cosine squared theta. And of course, negative one of those and another negative one of them gives me negative 2 of them. Boom. What's that? Yes, we will take it through the steps one more time. Up here in green, I have a Pythagorean identity. The Pythagorean identity, right? Sine squared plus cosine squared equals 1. I know I said it backwards, but for some reason I always say sine first. What we needed, because remember, you are allowed to remember where you're going. We were going to a place where there were no sine squareds. So what we needed was a way to replace our sine squareds with something that was cosine squareds. This way, we had no more sine squareds, and we just had more than one cosine squared going on somewhere. So up here, what we do is we go, fine, let me get sine squared by itself so I can make a substitution. And when you get sine squared by itself, all you're doing is subtracting this cosine squared from both sides. You get this Pythagorean identity, which is just a way of replacing sine squared thetas with things that involve cosine squared thetas. So we took this 1 minus cosine squared theta and put it right there, since they were equal to one another. That was the trick. And this version of the proof is so much nicer than what's on my paper. Funny enough, it did get to here though, and then make the one solution. So this stuff that we did right here, which was McKinley's suggestion of replacing my 1 plus cotangent squared with cosecant squared, was a lot easier than what I did. And I'm going to be honest with you, the reason why I did what I did was because of the title, working with common denominators. But yeah, I'm going to show you. Can I show you now? Everybody's finished writing this? Who likes fractions? You see, what I did was I replaced all my cotangents with cosine over sine. And then, And then I said my ones were sine squared over sine squared. So now up here I have a common denominator, which is what Max was saying. Where's the common denominators? This is what the authors meant. Because I saw the title, I went ahead and said, okay, let's find some denominators, and I went after fractions. And you can combine it like that. And then the bottom combines to this, which is nice because this is a Pythagorean identity. When you divide by a fraction, you're multiplying by its reciprocal. So the sine squared's canceled. This just equals 1, so it doesn't matter, leaving me with that. But look how much easier we got to that result by using Pythagorean identities. So nice. So much better. And that is it. So the question becomes, if I'm going to do some more questions from the book, is it beneficial to have it in the video? You think that's useful or no?
Yeah.
All right. Well, let me pause the video while I track down some questions from the book then. All right, we've identified a question to do from the textbook. We're going to tackle number 29 because it's very similar to number 30, and number 30 was on the homework. So what we have here is cotangent squared x minus cosine squared x. We're trying to prove that it equals cosine squared x cotangent squared x. So let me read the directions. Prove the identity. Very simple. There we go. Meaning the directions were simple. Not that doesn't mean the proof is simple. Okay. Remember, we have the ability to work on both sides if we'd like to, independent of one another. But I really don't like to do that unless I'm forced to. I'm a purist. Let's say I enjoy starting on the left and ending up on the right. So let's see if we can make that happen. Right off the bat, how would I approach this? I would deal with this cotangent squared. That's how I would approach this. I would write this as a fraction. Why would I do that? Honestly, because it's the first thing that comes to my mind that I see as being useful. I'm on the hunt for maybe some Pythagorean identities. I know I'm going to be ending up with some products here, so I'm thinking I got to get some denominators to cancel or something like that. That's just the thought process. I could be completely wrong, and I'm not afraid of that. Cotangent is cosine squared over sine squared, right?
Yeah.
Okay. So cosine squared over sine squared. Also, I'm not afraid of fractions. And, oh, well, I need common denominators, don't I? Clearly, the common denominator is sine squared x, right? So what I'll do is I'll multiply the top and bottom by sine squared x. And then we can see what happens. The top, the numerator, will now be cosine squared x minus cos squared x sine squared x. The bottom of this fraction will just be sine squared x. All right, well, we are allowed to look ahead to the future. We're allowed to. We could see that eventually we're going to end up with cosine squared times something else. I'm looking at the top of this fraction, and I am seeing that cosine squared x can be treated as a common factor. And I can factor this numerator. So I'm going to pull cosine squared x out, and I'm going to hope that what I'm left with will somehow cancel the sine squared or turn into cosine squared over sine squared, something like that. What it's going to leave me when I factor it from this numerator is 1 minus sine squared x. And guess what? I'm just going to go ahead and remind you guys of the Pythagorean identity here, that cosine squared x plus sine squared x is 1. And looky here, 1 minus sine squared x. I can get 1 minus sine squared x from this Pythagorean identity simply by subtracting sine squared x from both sides. It'll give me that cosine squared x equals 1 minus sine squared x. So this can replace this set of parentheses. That's going to give me cosine squared x times cosine squared x. I am not going to make that cosine to the fourth. And here's why. my answer has a my goal has a cosine squared in it. And I would love to keep this part of it. Hey, whoa, 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 whoa. Cosine squared over sine squared. Yo, that's cotangent. Yeah, we're done. This says cosine squared x times cotangent squared x. And number 30 will be done in a similar fashion. These 1 minus sine squareds and 1 minus cosine squareds are very powerful tools for you. Be on the lookout for them. They are how you change things from sine to cosine or from cosine to sine. They're your friend. We have 8 more minutes. What's up? Yeah. Cosecant squared minus 1 is cotangent from one of the other Pythagorean identities. Cool. And you know that's great. And you did that before I got started. Clearly, that's awesome. Now, why didn't I do it that way? You ready for the honest answer? I don't have the other Pythagorean identities memorized. Honestly, that's why I didn't do it. I don't have the Pythagorean identities that involve secant, cosecant, tangent, and cotangent memorized. I just don't. You don't need to, but if you do, hopefully you noticed how useful that was from what Breyer said. She's absolutely right. I would have been afraid to go down that road because I don't know them. I could build them, but I'm so comfortable with these that I've just taught myself how to get to them. But that's awesome, Breyer. Fantastic. That's great. Woot. Which is also why in the notes, when McKinley was like, hey, isn't that a Pythagorean identity? That's why I didn't do it that way, because I don't know them. Because you don't need to. Hopefully you're noticing that you don't actually need to know them as long as you know where they come from. Ah, you guys are smart. I love it. We have time for one more. Someone shout out a number that was hard. Not all at once now, okay? This is going to be an epic YouTube video. Nobody else was struggling with the homework, huh? 36. You know what it tells me? It tells me that most people weren't doing the homework. That's what it looks like to me.
I did a little bit of it.
Did a little bit of it. Let's see. 36 is remarkably similar to 45. So I'm going to go over to 45. They are very, very similar. I don't even know if I have enough time or space here, but we're going to give it a shot. This is number 45. Gives me tangent x over 1 minus cotangent x. And then plus cotangent x over 1 minus tangent x. Our job is to prove that this is equal to, what have I done to myself? 1 plus sec x cosec x. Okay, guys, I chose this question to spook myself because tangents and cotangents, I'm aware that they have Pythagorean identities that I have not committed to memory. Time for some personal growth. We ready for this? It's time for some personal growth. Rather than turn everything into fractions, which is my initial reaction that I want to do, I want to turn everything into fractions because I don't fear them. Let's see if I can't do some Pythagorean identity stuff. Well, no, as it stands, there aren't any because there's no exponents. But we all know and are aware that there are Pythagorean identities for cotangent, tangent. So let's go ahead and build some. Cosine squared x plus sine squared x equals 1. Let's get one for cotangent real quick. In order to get cotangent, we have to divide everything by sine squared, because cotangent is cosine over sine. So we're going to divide by sine squared x, excuse me. Let's see what we get. We get the Pythagorean identity that cotangent squared x plus 1 equals cosecant squared x. And be darned, we can't use the cotangent one. Shuck, shoot, darn. Didn't work, did it? Maybe the tangent one. Or maybe not. I don't know. So I'm pretty sure that the tangent one is tangent squared theta plus 1 equals secant squared theta. I think I have that one memorized. Is this the other one? Tangent squared theta, oh, I wrote x, plus 1 equals secant squared x. Okay, yeah, that's what you get if you divide everything by cosine. So there you go. Tangent squared, yeah, you see the problem that we're having here? Yeah, it's not going to work. Okay, well, that didn't work. Then that means that I'm just going to go ahead and go with my old buddy fractions. Unless somebody sees a better way, that's how I'm going to do it. I am going to say it would be nice if these two things had a common denominator. And I know that cotangent can be represented as a fraction just like tangent can be represented as a fraction. But I don't know, let's see. Let's turn everything into fractions. Tangent is sine over cosine. And on the bottom here I have 1 minus cosine x over sine x. Okay. If I had this down here as a single fraction, then I could use keep, change, flip, and something magic might happen. And I'm going to do the same thing over here. Yeah. Just because I'm running low on time, the common denominator here is sine. This is sine over sine. You see that? So this is going to give me sine minus cosine over sine. And then over here, I'm going to need a common denominator. That common denominator is cosine. This is cosine over cosine. So that means down here, I have cosine minus sine over sine. Okay. Good old keep, change, flip action. Run low in space. But I have to do the keep, change, flip thing twice. Uh-oh, nothing canceled. Yikes! That is no good. I'm listening. Oh, yeah, thank you. I wrote the wrong one. Good catch. That's what happens when you're in a rush. So I'm not going to have time to finish this proof, but I can tell you what I see. Here's what I see going forward. This is going to be sine cosine minus cosine squared. This is going to be sine cosine minus sine squared. Those are darn near the same thing. Okay. And up here and here you would have more replacements. It's got a lot more work to go, but that's what I'm seeing. I'm seeing a lot of sine squareds and cosine squareds. Alrighty, guys. Have a good weekend.